The doors have now been sealed. A nerve toxin will slowly start seeping. No, I'm just kidding. But we are going to get started. My name's Chase. Hold on, we're going to turn this down just a little bit. We're going to talk about neural networks. Woo! Yeah, I'm excited about it. I hope you're excited about it. I'm Chase Oakwine. That's Chase Oakwine. That's Chase, like the bank. Oakwine, like oak tree, bottle of wine, but with a spelling that's like gold coin. So that's cool. But Chase Oakwine, I am a technical evangelist for AppDynamics. We are an application performance monitoring company. That's all I'm going to say about that for now. We'll talk about that later. But right now we're going to talk about neural networks. That's neural networks. People are super excited about neural networks. People are pumped and have been for a couple of years. It's not really surprising whenever we think about DeepMind, Boston Dynamics, Watson winning Jeopardy. Like that's it's pretty cool where we're at in technology right now. Although I'd have to say the Boston Dynamics dogs do scare me only because I watch Black Mirror and just terrifies me. So, but there have been some cool advancements in medicine, predictive analytics, material science. You name it, there's very few industries and businesses that haven't in some way been touched by machine learning and neural networks. So first I want to set some expectations. This is a 100 level talk. This is going to be fairly high level. My goal, ultimately, I have one goal for you guys, and that is this. At the end of this talk, I want to kind of demystify some of this stuff and give you a sense of, oh, okay, I see how that can solve problems. I can understand that, but we're not going to go deep down into the maths because ultimately the maths aren't the most important part. They are important, but sometimes they work as a stumbling block. And so moreover, I want to give you some abstract ideas on how you can think about thinking about neural networks that hopefully by the end you go, yeah, that makes a ton of sense. I get this. So first we got to ask the question, what exactly is a neural network? Well, the first thing it is just a math formula. And it sometimes doesn't feel that way because with all of these amazing things that we've done, all of these different industries that have been touched, all of this power, how can that just be a math formula, right? It's sometimes hard to imagine that it's just a math formula. We expect it to be like a framework or a library, especially for developers. You know, we expect it to be like a whole suite of things. But really, at the end of the day, it just is a math formula. The second thing, loosely based on the brain. So in the earlier parts of the last century, as we were coming up and as we were understanding the way that the human mind works at a cellular level, some mathematicians later in the century were saying, hey, now that we kind of see how that works, what if we modeled that mathematically? Could we do anything interesting with it? Which brings us to our third thing. They're a lot older than you think. That while they've had a lot of press over the last 3 to 5 years, they've been around since 1972. The first neural network was created in 1972. And so it's been around for a while. It's just been accelerating a lot recently. But why are they so popular right now? If they've been around for 40 years plus, why does it just feel like now we're starting to get these advancements? The biggest one is available compute. It's sometimes easy to take for granted just how much computational power we have right now compared to any other time. So take 1998, right? We didn't even really have dual core chips yet. So on two cores on a single die. That wasn't a thing, right? We had multiple sockets on a board, but not multiple cores on a socket, right? And so if you take something like an NVIDIA 1080 GPU, it's going to have upwards of nearly 4,000 cores on it. So each one of those cores runs the equivalent speed of a desktop tower from 1998. So if you think about that, if we were to go back into 1998 with that amount of compute, it would cost us $80+ million for that much compute. So that $800 is a bargain, is what I'm saying. The second thing is frameworks. Frameworks have given us the ability to kind of lift and shift the responsibility from just raw mathematics to not having to care so much about that and not having to care so much about how do we distribute this problem out to all of these different processors and instead focus on the problem itself. which has been a huge boon to accessibility. The lower that we can the lower that we can make the barrier to entry for this stuff, the more imagination that it spawns, because then we don't have to worry so much about those higher order functions in the brain where you have to be really meticulous and really analytic. We can play. We can be children at heart. We can really like get in there and just try and fail and try again. And ultimately, that's where most innovation comes from, is that process. And then lastly, automation. Businesses are trying very hard to get as much value as they can out of as few resources as they can. And so we've been automating, well, for a couple hundred years at this point, well, 150 years at this point. And as we've continued that process, we've had more and more need for more and more automation, and automating in ways that we hadn't been able to previously. But with the culmination of this much GPU, the driving force of business, and the ready accessibility to practically everyone for getting involved, it's made kind of a groundswell for neural networks to thrive and be an exciting space. We're going to talk about 5 parts of the neural network. Now, those of you who maybe already know a little bit about neural networks, you're going to go, hey, this isn't in there. Okay, that's fine. It's not important, right? We're going to focus on these 5 key parts, because with them, you're going to have a good enough understanding that you're going to be able to go and start expanding and exploring different things and different patterns, practices, et cetera, within this space. And they're these: inputs, outputs, weights, bias, and hidden layers. But really, we're going to focus on just these 2 first, inputs and outputs, because at the end of the day, that's the core of what a neural network is. Neural networks are basically maps. So we have some data, and we want to map that data into something meaningful on the other end. If we think about the problem space from that perspective, it becomes a lot easier. But really, that's all they are, is trying to map one set of data to some other set of data. So inputs are what we already know, what we know today. So for you and I, this is a picture of a dog, but for a computer, this is not a picture of a dog. This is a bunch of individual pixels, and it's not even a pixel, it's just a number, right? It's 3 numbers that represent a pixel. And so for a machine, it's just arbitrary. It doesn't mean anything. There's no inherent value to it. But for us, there is. There are things that we know. And so our outputs are what we would like to know about that image. So in this case, what is it classified as? Is it a dog, is it a cat, or is it a baby, right? So our inputs are what we already know. Our outputs are what we want to know. So in the case of this image, we want to know that this is a dog. Or in the case of this image, we want to know this is a cat. Neural networks map inputs, outputs. So the way that we do this is we take a whole bunch of data that we've already taken a look at, and we've already analyzed, and we've said, here are the things that we know about this data. And we want to be able to know that about other data that we've not done that to in the future. So we want to map what we already know, what we've taken the time to discover, so that the computer can map those relationships, map that process to know that when pixels are this way, they are a dog. When pixels are that way, they are a cat. So how do they do that? How can you map something so vague as pixels to something so meaningful like a dog or a cat or a person? So that's where weights come in. So why do we need weights? Why must we lift, bro? I think it's an important question. So weights are used by inputs to control the flow of information. So what weights let us do is they let us change the shape and nature of the information that's coming from the inputs so that we can do things with it. Some of those things we can do, we can let the data flow just as it is. Or if we want to, we can restrict and throttle that flow of data. We can stop it entirely. Or we can amplify that flow of data. So as data flows through our system, we can change the nature of that data. For me, I find it useful to think of it like EQ on a soundboard. So if I take sound that's coming through a sound system with just a 3-band EQ that we're all familiar in our cars, high, mid, low, I can change it a little bit. I can make it a different output than it was originally. But if I have something like a 30-band EQ, I can get very fine grained with how much audio is coming through that. And I can do things like isolate the frequency of a hi-hat. So the only thing that's coming through that sound is a hi-hat. And this is just with an analog board, but ultimately that's what we're trying to do with neural networks, is to filter and change data around so that we get something entirely different than what was put in, right? And so we're going to talk about the color wheel. So now for those of you who may be colorblind in the audience, I have tried to label everything, but we are going to talk about the blending of colors because I find this to be a good visual representation of the point that I'm trying to get across. So let's say we've got equal parts red and blue. Well, that's going to mix to be magenta. If I cut how much blue, I'm going to get more of a rose color. If I cut how much red, I would get a violet color. And so these connection points, these are our weights. But weights are a little bit different because instead of, well, so we can just do all of one or all of the others. We can do blue or red. But with weights, our weights are in between the input and the output. So we can then change the structure even further. So we can do things like if we have a weak signal that's coming in from our red, we can boost that signal and make it a proper red. Or if we wanted to, we could saturate that signal, right? And by saturating that signal, we then all of a sudden open up a whole new color horizon where now we get into pinks. Or if we add a little bit of that blue back in, we're now in a pink spectrum, or a neon pink, if we change the values further. But with just these 4 values, we're able to create an incredibly wide variety of different colors and hues, just from the mixing of those 2 sets of data in different ways. So the question that people often ask is, so we know that we have to change these weights as a part of a neural network. Who does that? Is that something that I do? Do I have to get in and tweak that? And the answer is no. A neural network trains the values of its weights by taking in those instances of objects that we already know what the inputs and the outputs are, and it gradually changes the weights over time to make them match up. The mapping, this relationship between those inputs and outputs, that's the network part of a neural network, which if we start to look at a neural network in this way, we can see that it's very similar to what we think of as networks as technical engineers and things like that. And so to make this make a little bit more sense, this is what's called a dense network. A dense network, each input is connected to all of the outputs. So this input is connected to all those outputs, this one to all those outputs, this one to all those outputs. So whenever you hear the phrase dense network, that's all that means. All of the inputs are connected to all of the outputs. So let's talk about triads. Triads on a color wheel are segments like this. We have primary, tertiary, and secondary colors. But to keep it basic, we're just going to focus on the primary colors. And we want to find a triad. So basically given 2 inputs, we want to know what the third input should be. So we can set our weights accordingly because for red, we know that the other 2 that make that up are blue and yellow. For blue, the other 2 that make up that are red and yellow, and for yellow, blue and red. And so the thing that's interesting is by setting those weights in that way, we've effectively trimmed our dense network. By setting some to 0, because no data is going through, they don't really matter. So while those connections are still there, because no data is passing through, it has the same effect as pruning that data. So for classification, our goal is typically to pick whichever output has the highest value. So in real world practice, whenever we're trying to classify things, we're just picking whichever value has the most. And so if we take those values and we plug in an example, we can see that yellow has the highest, and that's exactly what we're looking for. And so this is in effect how neural networks work. When it's just building on this to do more and more complex structures and more complex questions. This is a fairly simplistic question. But what if we want to adjust it further? What if we don't just need the highest value? What if we need it to be more absolute in its nature? What if we need it to absolutely be this or that? Well, that's where the bias comes in. So our bias lets us shift values around in the space. So if we were to add a -1 to all of these values, all of a sudden we now go, we're either absolutely yes or absolutely no, right? And so that's all the bias does, is it just shifts values in a direction, plus or minus. With this setup right now, we can only ever solve simple problems. But what if we have more complex problems? What if we have the types of problems that they're trying to solve at IBM, Google, Boston Dynamics, and other places? So that's where hidden layers come in. And this is something that can sometimes be confusing for people when they first start looking into neural networks. They're like, hidden layer, what's a hidden layer? I don't understand it. It sounds confusing, I don't like it, I don't want to do it. But I can promise you, it's not scary. So if we think of inputs and outputs, let's say we wanted to take a simple math problem that's just y minus x times 2. So if we were going to break this down into like programming, we'd have two basic functions. We'd have two steps. First, we'd compute the difference, y minus x, and then we would multiply that times 2. So the problem is that with this amount of input, with just inputs and outputs, we can't set the weights in any way. There's no possible way that we can set the weights in this particular configuration that we would get a solve for this problem. We could try everything from positive infinity to negative infinity on both of those weights. We would never get the right answer. But that's because we need to add more complexity. So if we add some additional nodes, if we add some additional inputs in there, all of a sudden, with the weights, we can get to the answer that we want. Not only that, if we change the input values, we haven't changed the weights at all, but we've created a system now that can reliably reproduce that result. And so now we have a reusable network. Whenever we think about it structurally, we start at the top and the bottom with our inputs and outputs, and then we have hidden layers in the middle. So whenever you dig into this further and you start looking at diagrams and things, you may see it flipped the other way to where it's like horizontal instead of vertical like this. But this typically tends to be how we think of the architecture for our network, is how many hidden layers, how many nodes in each of those layers, and how they connect to each other. But at the end of the day, really all we're doing is taking inputs, mapping them to outputs, which then become inputs that we map to outputs, which then become inputs that we map to outputs, right? But really the only inputs and outputs that we care about are just the top and the bottom. That's why these are called hidden layers, because we don't care. We don't know intrinsically what those values should be. That logic is hidden to us. We don't necessarily have to know. We just have to know what our starting point and our ending point are. So this isn't dissimilar from our programming example, where we have inputs and then we have an output that's the difference, and then we have inputs and then our outputs, that's the difference. So whenever you can think about the problem space in that way, it makes it less scary. It makes it a lot easier to go, okay, well that's not voodoo, that's not magic, that's just simple logic. So we don't know in advance what these hidden values are. Only the ins and outs. That's the big thing that we care about. We care about what the inputs are, what the outputs are. This is considered a deep network. So whenever we add more of these hidden layers like this, that's considered going deep. So whenever you hear the phrase deep network, that's all that means. There is also the notion of a wide network. And so a wide network is in favor of, in lieu of adding depth to our network, we add width to that network, where we basically just have a single hidden layer and a lot of values that we can place in there. And there are some pros and cons to each that are kind of beyond the scope of this. Neural networks can, in theory, approximate any mathematical function. That's why they're sometimes known as universal function approximators. Now, where that gets really cool is that any function can be ultimately turned into a math problem. And that sounds not true off the cuff, but whenever you think about what's going on in your computer, you're doing all these rich activities, you're displaying images, you have the internet, you have all these things, which are ultimately drilling down to very simple math problems down at the processor, right? So everything that's happening on the processor level is just basic math, just addition, multiplication, subtraction. And so you can feasibly represent any function. Now that said, there are some functions that might be so computationally expensive to find the mappings for that it wouldn't be feasible to do in a lifetime. But from the process itself, you can, in theory, approximate any function. So those are all of the parts. Our inputs, what you know, outputs, what you want to know. Weights kind of connect the two. Bias shifts the value, and then our hidden layers provide complexity so that we can ask richer and richer problems. So how do you do it? How do you make one? Well, there's a lot of different choices. We got MXNet, TensorFlow, Caffe, CNTK, all these different things. Sometimes it's hard to decide on something through the mix. And I'll say this, whatever you use and whatever you're comfortable with and whatever you like using, that's the right choice. Like there is no, I'm very undogmatic about my choices. Like if there's something that you're using and it's effective for you, it's a good choice for you, please use that. For me, I like to use Keras. And the reason I personally like to use Keras is it's an abstraction layer on top of other engines. So TensorFlow is basically an abstraction on parallelizing problems. So it's an abstraction on top of hardware that says, how do we take this problem and distribute it over a bunch of cores or a bunch of machines? Keras is kind of one step above that says, how do we make something that's a little bit more person readable and abstract that to an engine like TensorFlow or PyTorch or Theano or one of these others. And the reason I like that is that as the backend technologies change and improve, my code that I write doesn't have to. So not sponsored, just my own take on it. The other thing I like about it is basically like assembling building blocks. I don't have to care so much about the math. I just care more about here are the different types of things that I can connect together, and I'm going to play around, I'm going to connect them up, and I'm going to see what works and what doesn't. So what if we wanted to make our very simple network? Well, we can do that in 10 lines of code, front to back. So we've got some sample inputs and sample outputs. The reality is you would want many more inputs and many more outputs than this. This is just 2 examples. Then we define a model. So it's going to be a sequential model. And so what sequential means is that each time we do an add, it's going to be the next layer from our diagram. So we're going to take from our model, we're going to add a dense layer that's going to take 2 inputs. It's going to have 2 units. We're going to add a dense layer that's going to have 1 unit. We're going to add a dense layer that's going to have 1 unit. And then we're going to compile it and fit it, which we'll discuss this part in a minute. But this is the meat of it. This is the bulk of what you'll do. And so this model makes it really, really handy to build out things quickly. So if I wanted to all of a sudden have 2,000 things, I just put a couple zeros on there, right? It makes it a lot more approachable to building out these models. But to represent this visually alongside with the code, we have our inputs, we have our dense, and our dense. And so this is what we were building out on that code. So it's pretty simple. Like there's nothing here. Does anybody feel like they can't, like they don't understand this? Like this doesn't make sense, this part of it? No? It's because it's pretty straightforward. We're just taking inputs and outputs. So inputs, output, which that becomes the input for this, which becomes the input for this, and then that's our output. And that's it. So let's talk about this. So loss and optimization is the process of training. So whenever you hear the phrase loss and optimization, the goal is we are training our neural network to map that data from one type to the other. Loss is the measurement of how far a model's prediction is from what you wanted. So as you're providing samples, it's going to start out and it's going to be really, really bad at it. And you need to have some measure of knowing just how bad it is and if you're getting better or worse. And so what happens is as you go through, you take this error, and the goal is to minimize it. We want to minimize loss over time. Your optimizer is the function that does the adjustment of the weights to minimize that function. So each time it runs through an example, it says how far am I off? How can I adjust the weights to make it closer? Do it again. And it just keeps doing it again until you have reached a level of loss that is acceptable for your individual project. So as a beginner, for most models, start, if you're using Keras, use mean squared error and Atom optimizer. We don't really have to go into what those are. 9.99 out of 10 of your problems are going to be solved with that. And especially for just getting started, it's way better to like not worry about that, get in, worry about your inputs and outputs, start playing around with data, start throwing data at it, and make sense of that before you start trying to muddle with all that. Because what will happen is if you get too deep into this stuff early, you'll miss the important bits on building with the inputs and outputs, and you'll start solving the wrong problem. So you start saying, well, if only I had a better error function, if only I had a better optimization function, then my problem will be solved, when it might be a problem with your inputs and outputs. So let's talk about cows. So I'm from Arkansas originally. I was born and raised, well, I was born in Louisiana and raised in Arkansas. Very rural community. We were a farming community. And I find cows to be important for learning. So let's say we wanted to know what kinds of cows these are. And I know what you're thinking, Chase, those are all the same cow. They're clearly brown. But they are. They're each a different type of cow. So we could use what's called a classifier. So with a classifier, we can take some data. In this case, we're going to take a 72 by 72 set of black and white pixels, and we want to know what kind of cow this is. And so we will then feed that input into a hidden layer that's going to have 50 units. We're going to feed that into our output that has 3, and we need to be able to know what kind of cow it is. So the way that we're going to represent that is we have text that we know and understand, but we want to represent that text as numbers. And so we're just going to use a 0 or a 1. And so in this case, our 1 represents a longhorn, and it is a longhorn, not a Guernsey or a Highland cow. But what if we wanted to predict milk sales? What if we've been in the booming business of dairy sales, and we want to see how we're going to do it next month? So this would be forecasting. We do forecast modeling through neural networks as well. So let's say we wanted to take our year's worth of data, and we want to try and guess what we're going to do next month. So our inputs, we can say just do 6 months of sales. And so we just take 6 values from our sales, and we want to try to guess the 7th. And so what we can do is take, let's say we've got 20, 30 years worth of data. We can chunk that up into months, and we can just take 7 points of data together at random from that. 6 of them as inputs, 1 of them as output. Train the network to guess based on those 6 what the 7th one might be. And that would be our next month's predicted price. So this is like the simplest form of forecasting. There are other structures that we can do on top of this to further refine that. Now the difference between this one and the last one we were looking for a solid number. This one, we're looking for a value. This is what's called a regression problem. So whenever you're looking for a choice, that's a classification problem. Whenever you're looking for an exact number or an estimated number, that's a regression problem. What if we wanted to estimate the price of a cow at auction? This also goes more towards regression. So in this case, we would take all of the facts that we know about the cow being featured, and we would take the weight, the age, the breed, the diet, whatever, any kind of metadata that we could possibly know about that cow, and we feed it in. And so now we've stopped caring about how many, because the amount of units in the middle is not as important as it is to play and try and experiment. And then output, we want the estimated price per pound. And so from all of that data, we can map those features into our meaningful output. Now, what's really cool, if you want to get the advanced level stuff, flip it around. Then you can map estimated prices to features, and then you can see for higher valued items what features show up more prominently, which you can use as a way of kind of predicting what you should focus on, right? And so you can absolutely flip that around, because again, we're just mapping inputs to outputs. It doesn't matter what the inputs and outputs are. You can flip them around all day. So what if we wanted to automate a cattle auction? So this is where we get into reinforcement learning. And this is going to be like a super simplified version of this. This could be like a whole half-day workshop on this. But so basically with reinforcement learnings, we take, similarly to knowing the price of a cow, we want to take all of this all of the data that we know right now. But in the case of an auction, it's things like bid prices, cow info, sentiment of the audience, whatever we can get about what's happening right now. And from that, we want to guess an action. Whether we wait, whether we raise the bid, whether we take the bid, whether we do all of these different things, whatever our possible actions are. And the goal with reinforcement learning is to go from that state to that action, and that will give us a new state and action. And so the idea is, over time, you want to focus on what gives you the highest level of reward. So ideally, we're optimizing to make the most amount of money per cow. So that's our reward function. So ultimately, our goal is to find the best actions that will lead to the best states that ultimately yield the best rewards. That's how reinforcement learning works. So I'll say that once more for posterity. So we want to take some known set of data. We want to take what's going on right now. We want to map that into what we're going to do. And from that, we want to be able to guess what that will then do to the state and what that will outcome as a long-term reward. So ultimately, our goal with reinforcement learning is to optimize to some far future reward. So the way that we're using machine learning and neural networks over at AppDynamics, we're an application performance monitoring suite. We work with all sorts of platforms from .NET, Python, Java, you name it. We've made huge investments in machine learning over the last couple of years to improve our products, and it's had a big impact on our customers. We're about to launch a whole new suite of tools that take what we've done from kind of basic machine learning in the past for anomaly detection to so the goal has been for the last few years to get us up to knowing kind of what's happening right now and why it's happening right now. But where we're going is we want to know what's about to happen, and not just in a few minutes, but in a few hours or a few days or a few months. We want to be able to say pretty clearly that these lines of codes, these systems, these services are going to cause these problems down the line with these hard drives, with these CPUs, with your total utilization, with your customer impact, with this amount of loss and profit, et cetera. That's our ultimate goal as an organization. We want to take as much of that work out of your hands as possible. And the reason I say that, not only because I work there, but I say this to encourage you to think about use cases in your own organizations where you might be able to leverage these types of technologies, because the value is there. Companies are being impacted daily by investing in these types of technologies. But that said, there are some things that you have to take into reasonable consideration. This is not like usual programming work. You're not looking for like, I want to be able to click this and it turned magenta, right? Like that's not what we're looking for. And so it's a lot closer to R&D than anything else. It really is research. So whenever you're doing this kind of data science work to add products and enhance what you do as an organization, you have to treat it like an R&D budget. Sometimes that's hard. Sometimes that message doesn't get relayed properly to the executive heads whenever you're having those discussions, and so they feel let down whenever they aren't making these huge achievements in a month or two, right? Experiment, hypothesize, try something. If it fails, go on to the next one. Keep doing the scientific process over and over. Have an idea, try it out. If it doesn't work, that's okay. Learn something from it, move on to the next experiment, and keep doing that. That is basically my closing thought is don't be afraid to fail. Failing's good. Failing's great, especially in this business. That said, try not to fail in production, but before then, whenever you're just learning, whenever you're just trying to like get your feet under you, don't not go out and download these tools and try and play for fear of, well, I don't have a math background. I'm maybe not good enough. I don't know. That's not a good reason, right? You absolutely can do this stuff, and you may not get it right away, but there's a whole community of people out there on Twitter, on LinkedIn, all over the place that are way more than happy to help you out and make sure that you're successful. Because ultimately, I think all of us want each other to be successful. So that's where I'm going to leave it. Go be dangerous. And I'll stick around for questions. I got swag if anybody wants some. And with that said, I'll let you guys clap.